This is our first chapter. We're going to learn all about polynomial functions. And in this first lesson, we're going to learn about the most basic type of polynomial function called a power function. So let's get going. Oh, and before we jump right into this course, I have a few slides here just reviewing some key things about functions that you're going to need to know moving forward that you would have learned in your previous course. So you need to know, first of all, since this is called the Advanced Functions course, you need to know what a function is. So remember that a relation between an x and y value is a function if for every x value, there's only one corresponding y value. So each x value should only be able to generate one y value. And we can easily test to see if that's true if we have a graph by using what's called the vertical line test. A relationship is only a function if it passes the vertical line test. And on the right here, I have an example of something that fails the vertical line test. It fails the vertical line test because this vertical line drawn here in red goes through this relationship at 2 points. That means for the x value of 6, there are two different y values you could get. You could get a y value of 0 here or a y value of 4 there. So that single x value of 6 outputs two different y values. So that means it is not a function. This relation here, not a function. It's only a function if it passes the vertical line test, meaning a vertical line drawn anywhere along the path of the graph intersects the graph at no more than 1 point. Next thing you need to remember is about domain and range. So domain of a function is the complete set of all possible values of x. So it's basically what values could you input for x and get a value for y. So what input values are possible? Or if we're thinking graphically, we're looking where does the function exist horizontally? The range of a function is the set of all possible resulting values of y. So it's what outputs can you get the function to give you. And if we're thinking graphically, we're thinking about where does the function exist vertically. So let's do a quick example reviewing domain and range. So I've given you this quadratic function here. Let's look at what the domain and range of this function is. And it may be helpful if I go over to Desmos so that it'll clearly show us the x and y values the function can take. So here we go. Here's that same function. And what I have Desmos showing me this point and the point's x and y coordinate. Now, when we're thinking about the domain of a function, we're thinking about what x values could I input into the equation and it be able to give me a y value. Well, if we look at this equation right here, we can plug anything we want in for x. There are no restrictions on what we could plug in for x. Any value of x we plug in, it'll be able to output a value of y for us. Right? No matter what I plug in for x, and this slider here is letting me plug in different values for x, and down here it's showing me the y value, it's showing me the output. But what I'm showing you is we can plug in anything we want for x, and it's going to give us a y value. There are no restrictions on what I could plug in for x. And if we look at the graph, it's just saying this function exists everywhere horizontally. It goes forever to the right. Like if I keep moving right, this function's still going to be there. And if I keep moving left, this function is still going to be there as well. I may have to look up high, but it's still going to be there. Plug anything you want in for x, you'll get a value for y. So for the domain, we would say the domain, x is any real number. Or we're going to learn in this lesson, there is another way to write domain and range using bracket notation. We could just write it goes from negative infinity to infinity. That's the set of x values that work in the function. Anything between negative infinity and infinity will work. That means any real number. Range, however, for this function, what y values, and remember f at x, that's just function notation for the y value at a given x value. What y values can this function output? So when we're plugging in these numbers for x, right, we can plug anything we want for x. What y values can we get? Well, if we look at this point, pay attention to the y value, or look over here, I have it telling us the y value here as well. As I move this point, what are the y values? Well, it's 45 there, about 30 there, about 8 there. Notice the lowest it ever goes is 3. That's the lowest y value I could ever get. As I move this point left, the y values start going back up again. So there's no way, there's no value of x I could plug in to get a value of y lower than 3. And if we look vertically, right, this function is never below 3 vertically. It's always at a y value of 3 or above. So what we would say y can be any real number, but it has some restrictions. y can be any real number given, the vertical line means given, the y value is greater than or equal to 3. And we're going to learn a new way to write that as well. We could say the range would be any number between 3 and infinity, including 3. And I'll talk to you about these square and round brackets in just a little bit. But that's another way we could write the range. That's called bracket notation. Okay, almost done reviewing before we get into the new stuff. The degree of a function is the highest exponent in the expression. So this is what we call a polynomial function, and we'll talk about the definition of those in just a second. But this function, you would have learned in grade 9 that this function is a degree 3 function. How do we know that? Well, this term is degree 3, this term is degree 2, this term is degree 1, that term is degree 0. The degree of the function is equal to the highest degree term in the function. This is the highest degree term, it's degree 3. So the function itself, we would say, is degree 3. And one more thing that's going to be important in this course, not so much in this unit, but in the course these will definitely come up a lot, are asymptotes. An asymptote is a line that a curve approaches more and more closely but never actually touches it. So let's analyze this function right over here. This is the function y equals 1 over x plus 3. Actually, let's look at it in Desmos and talk about its vertical and horizontal asymptote. Okay, there's that same function, the 1 over x plus 3 function. Notice there are two asymptotes. There is a vertical asymptote at x equals negative 3. Why is it there? Why can we not plug negative 3 into the function? Like, watch, if I try and plug negative 3 into the function, what does it output to me? It says the y value, it says the function is undefined. It doesn't exist. Why? Well, if we plug negative 3 into this function, we'd get 1 over 0, and we can't divide by 0. So 1 divided by 0 is undefined. That's why x can't be negative 3. That's why we see a vertical asymptote at x equals negative 3. Okay, what about the horizontal asymptote? There's a horizontal asymptote at y equals 0. Why is there a horizontal asymptote at y equals 0? Why can we not get this function to output a y value of 0? Well, let's look at this point as I drag it. Pay attention to the y values. Right? The y value of this point is 1.4. And as I move this point over, it looks like this function's y values are getting closer and closer to 0. You would think for sure it's going to get to 0. But it doesn't matter how big of an x value we plug in. Like, let me keep moving this point over. Doesn't matter how big this x value gets. This y value just keeps getting closer and closer to 0. It'll never actually get there. It doesn't matter how big of an x value I put in. It just makes it get closer and closer to 0. See, the y value is still not at 0, and it'll never get there. It'll just keep getting closer to it. And if we think about this function, the bigger value we put in for x, the bigger the denominator is going to get. And you're going to get 1 over an insanely big number. You're still going to have 0.00 something, right? You're not going to ever get exactly to 0. You're just going to keep getting closer. And same logic if we go in the other direction. Like if I bring this point back and we go in this other direction to the left, it's going to keep getting closer and closer to 0 as well, but it'll never get there. So how we can tell that there's going to be a horizontal asymptote at y equals 0 is if our rational function, the denominator, is higher degree than the numerator. The denominator is a degree 1 function, the numerator is degree 0, therefore there's going to be a horizontal asymptote at y equals 0. And we'll talk more about that in future units. Let me just read these two sections to you here. They just go over what I talked to you about. So a vertical asymptote, division by 0 is undefined, therefore the expression in the denominator of the function cannot be 0. Therefore, x can't be negative 3 in this example, because that would make this become 0, which makes the whole function become 1 over 0, which is undefined. This is why you see that vertical asymptote at x equals negative 3. Horizontal asymptote. For the range, there can never be a situation where the result of the division is 0. Therefore, the line y equals 0 is a horizontal asymptote. For all functions where the denominator is a higher degree than the numerator, there will be a horizontal asymptote at y equals 0. Okay, that's enough review. Let's move on to the new stuff. Let's talk about what a polynomial function is. If we look at this expression right here, this is what a polynomial function is. Let's just define what all these letters stand for in that expression. It's a lot easier than the way this equation makes it look. N, the exponent on our variable x, is always going to be a positive integer. Here it just says it's a whole number. Let's more clearly define that. It has to be non-negative. It has to be a non-negative integer. So non-negative integer. X is our variable in this case, and these a's that you see in front of those variable x's, we call those the coefficients. And the coefficients are always going to be real numbers. We also just talked about that the degree of the function is, in this case, n, which is the exponent of the greatest power of x. And notice the terms, so the terms are separated by these plus signs, or they could be minus signs, but the terms are written in proper order. They're written in descending order of degree. So you should see the highest degree term first. So let's say this was a 5, the next term would be a 4, then a 3, and so on. You may be missing some terms, but it has to be in proper order. The coefficient of the highest degree term, this one right here, we call that the leading coefficient. That's really important. That's going to tell us a lot about the shape of the graph of the function. And then this term way at the end that doesn't have an x multiplied by it, that term is just the constant. If it doesn't have an x, it's a constant term. For all polynomial functions we work with, the domain is always going to be the set of all real numbers. There is never going to be a restriction on what we could sub in for x to be able to get a y value. So for polynomial functions, domain is always x is any real number, or in bracket notation, we could write from negative infinity to infinity. The range, however, it may be all real numbers if we have an odd degree polynomial function. We'll talk about that more later as well. Or it could have a lower or an upper bound, not both though. So there could be a restriction on the range. And then this bullet point here, the graph of polynomial functions do not have horizontal or vertical asymptotes. So we're not going to have to worry about asymptotes in this unit. Last bullet point, I just want to remind you that if we have a polynomial function of degree 0, so for example like y equals 7, that would just be a horizontal line. The shapes of the graphs are always going to depend on the degree of the function and also its leading coefficient. And we'll talk about that as we go through the unit. I've shown you a few typical shapes right here. Here are some shapes of different degree polynomial functions. And we're going to learn how are we going to figure out what we call the end behavior of a function. So if we have a degree 5 polynomial function, how would we know that it starts like this and finishes like this? How do we know it starts here and finishes up here? We'll be able to tell that from its degree and leading coefficient. And then as we work at getting the polynomial function into factored form, then we'll be able to figure out what this in-between section looks like. But the first half of the unit, we just start looking at end behavior of the functions. And in this lesson, we're going to go really simple. We're just going to look at power functions. Power functions are the simplest type of polynomial functions because they're just one term. So power functions are polynomial functions that only have one term. There's nothing added or subtracted after that one term. So in this power function, a is always a real number, that's our coefficient, x is our variable, and n is a whole number, and it's always going to be non-negative. So it'll be a positive integer. Example 1, determine which functions are polynomial functions. State the degree and the leading coefficient of each polynomial function. Well, a is not a polynomial function, it's a trigonometric function. It's sine x. So this one's not a polynomial function, it's a trig function. Part B is a polynomial function. And in fact, it's only a single term polynomial function. So this is a power function. So yes, polynomial function. It is degree 4, and the leading coefficient is 2. This is a polynomial function of degree 4, leading coefficient is 2. Part C, also a polynomial function. All of the exponents on x are non-negative whole numbers. All the coefficients are real numbers. So yes, that is a polynomial function. And this function is degree 3 because that's the highest degree term. And its leading coefficient, even though I don't see it, is 1. Part D, the exponent is the variable. So this is not a polynomial function. For it to be a polynomial function, the exponents all have to be non-negative whole numbers. In this case, the exponent is a variable. So this is an exponential function, not a polynomial function. Okay, I talked to you a little bit about bracket notation as I introduced to you domain and range. Sometimes that bracket notation we call it interval notation, but same thing. So there's different ways we can express ranges of numbers. It's very important to be good at expressing ranges of numbers as an inequality, but often people like expressing it in interval or what I'll call bracket notation better. So if we read this, you have to understand that that inequality notation means that x is going to be greater than -3, but less than or equal to 5. And on a number line, we could see that here. That would mean that set of numbers. Anything that's bigger than -3, but less than or equal to 5. And I filled in the circle here at 5 to include 5. And here at -3, the circle is open, meaning not including -3. So any number between there, including 5, is what this inequality is representing. This bracket notation is representing the same set of numbers. It's just another way of writing the same thing. It says any number between -3 and 5, round bracket means not including -3, square bracket means including 5. So if we summarize this, square brackets indicate that the end value is included in the interval. Round brackets indicate that the end value is not included in the interval. And sometimes if we want to express a set of numbers that go to infinity or negative infinity, we have to use the infinity or negative infinity symbols. We need to know what type of bracket goes at infinity and negative infinity. In fact, it's always a round bracket at infinity or negative infinity. And this is because we can never actually get to infinity or negative infinity. Infinity is not a number. It's just an idea about the biggest possible number we could get to. And we can never get to that. It's just a way of saying it goes forever. So it's not actually a number, so we can never get there. So we always use round bracket at infinity or negative infinity. Okay, we're going to fill out a chart together. We'll do the first 3 rows together, and then I'll get you to do the next 3 on your own. So in this chart, we are going to be looking at the first 6 power functions and just looking at their general shape and writing their domains and ranges. And we'll write the domain and range using the new bracket notation. So we've got degree 1, degree 2, degree 3, degree 4, degree 5, and degree 6 power functions. We're going to comment on domain, range, and then also describe their shape by talking about what's called the end behavior. So let's do the first row, y equals x to the 1. This is what we call a linear function. It's a degree 1 function, so it's a linear function. The domain of this linear function is going to be any real number, and that's what it's going to be for all polynomial functions. So of course that's what it'll be for all power functions. And we can write that either as x can be any real number, or we could write it in our bracket notation saying from negative infinity to infinity, making sure you have round brackets at both negative infinity and infinity. So write it either way. And if we think about algebraically, why is this the case? Well, I can plug anything I want in for x and get an answer for y. And graphically, this linear function is going to extend forever to the right and forever to the left. The range, there's also no restrictions on the range for this function. This function is going to go forever high and forever low. I can get as big or small a y value as I want, depending on what I plug in for x, because in fact x and y are equal to each other. So of course, if there's no restrictions on the domain, there are going to be no restrictions on the range. So for the range, I would say negative infinity to infinity as well. End behavior. This is the new thing that we need to talk about in this course, and this is what I'm going to really be focusing on for the rest of this lesson. End behavior we can describe in a couple of ways. We can talk about it in quadrant notation, which I'll do second, or first what we're going to do is talk about what's happening to the y values as x goes to negative infinity and as x goes to infinity. So as the x values I plug in get closer and closer to negative infinity, what's happening to the y values of this function? Let's turn to Desmos for this. So as x goes to negative infinity, what's happening to y? So as I plug x values into this function that get closer and closer to negative infinity, what's happening to the y values? Either look here, those are the y values, or you can look here on the point. What's happening to those y values as x approaches negative infinity? Those y values are also going infinitely low. They're going to negative infinity as well. So as x goes to negative infinity, what's happening to y? Y is also going to negative infinity. And you can think of x going to negative infinity, think of that as we move to the left on the function. So as I move the point this way on the function, what's happening to the y values of that point? They're going to negative infinity. So you can think of this, if it helps, as moving left, which means as x goes to infinity, we're talking about as we move to the right on this function. So as the x values get bigger, we're moving to the right on the function. So I'd write here, this means to the right. What's happening to the y values as the x values approach infinity? Well, as the x values approach infinity, okay, plugging in bigger and bigger and bigger x values, what's happening to the y values? Those y values are going to a positive infinity. So the y values are going to positive infinity. So that's one way to write the end behavior of the function, by commenting as x goes to negative infinity, where's y going to? And as x goes to positive infinity, where's y going to? The other way we can do it, and this is the way most people are going to prefer to do it, is to talk about what quadrant does the function start in and what quadrant does the function finish in. Before we can do that, we have to remember how we number the quadrants. This is quadrant number 1, this is quadrant number 2, this is quadrant number 3, and this is quadrant number 4. So when I say where does this function start, I mean as I move from left to right along this function, where does it start and where does it finish? So the function starts down in this quadrant and it finishes up in this quadrant. So we would say the function goes from quadrant 3 to quadrant number 1. We could say starts in quadrant 3, finishes in quadrant 1, or we can just we can write that in a short form way by saying Q3 to Q1. That's the end behavior of this function. It goes from Q3 to Q1. All right, let's try another row. Let's do the quadratic function, y equals x squared. So this is a degree 2 power function. Okay, here's our x squared function. Domain, this function gets infinitely wide. It exists everywhere horizontally. We can plug in anything we want for x and get an answer for y, right? There's no restrictions on what you could plug in for x. So domain, x is any real number. Or in bracket notation, it goes from negative infinity to positive infinity. Any x value within that interval would work perfectly fine. What's the range of this function though? If we're thinking vertically, this function never goes below a y value of 0. The lowest y value I could get is 0. I can get any y value bigger than 0, but I can't get any y values below 0. So we'd say the range would be anything from 0 to infinity, including 0. So we'd say square bracket, 0, comma, infinity, round bracket. Always round bracket at infinity. And I should mention, when you're writing these bracket notations, the smaller number always goes on the left, bigger number on the right. So 0 is definitely smaller than infinity, so that's why that went on the left. End behavior. What quadrant does this function start in as I move from left to right? It starts over here at quadrant 2, and it finishes over here at quadrant 1. It goes from Q2 to Q1. If we're writing it by talking about as x goes to negative infinity, what's happening to the y values? Well, as I move this point forever to the left, what's happening to the y values? Pay attention to the y values of the point. They're going infinitely high. We'd say they're going to positive infinity. Y is going to infinity. And same if I move this point infinitely to the right. So as x goes to infinity, what's happening to the y values? The y values are also going to infinity. Let's do one more row together, and then you'll complete the next 3 on your own. Let's do a degree 3 power function. It makes this little S shape through here. This degree 3 power function, once again, there's no restrictions on what I could plug in for x. So our domain would be any x value between negative infinity and infinity. Our range, well, this function is going to go infinitely low and infinitely high, so no restrictions on the range either. Negative infinity to infinity. Let's talk about the end behavior. Well, what quadrant did the function start in as I move from left to right? It started down here in quadrant 3. It finished up here in quadrant 1. So we'd say it goes from Q3 to Q1. If we're talking about what's happening to the y values, well, as x goes to negative infinity, as x is going to negative infinity, what's happening to the y values at this point? They're going infinitely low. So I'd say y is going to negative infinity. And as x is going to positive infinity, so as this point moves forever to the right, what's happening to the y values? They're going infinitely high. Y is going to positive infinity. All right, try and fill out these next 3 rows on your own. So pause it, and then in a few seconds, I'll show you the answers. Okay, hopefully you tried it. Now let's look at the answers. Just watch me fill them out and check your answers, make sure you're getting them right. Okay, there's the answers for the next 3 power functions. Now let's summarize the patterns you should have come up with here. So let's look specifically at all the even degree power functions. Look back at our table. So I'm talking about the degree 2, the degree 4, and the degree 6. They all had the exact same properties. They all went from Q2 to Q1. They all had the same domain and range. So we can summarize their properties here. It wouldn't matter, so let me just make an even degree power function, so degree 4. It wouldn't matter, notice this one starts at Q2 and finishes at Q1. It wouldn't matter what positive even number I made this, it's still going to have that same end behavior. Let me change it to 6, to 8, to 10, to 12, to 14. I mean, this kind of U shape at the bottom is getting more shallow and wide as the exponent is getting bigger and bigger and bigger. But as long as I keep it even, it's got that exact same end behavior, starting in Q2 and finishing in Q1. If I have an even degree power function, the only thing that could change that end behavior is if I do a vertical reflection of this. So if I make the leading coefficient negative. So if I make the leading coefficient -1 instead of +1, it flips it upside down. And now the end behavior is from Q3 to Q4 instead of 2 to 1. So let's summarize that. If the leading coefficient is positive, so like all the ones in the table we did, the end behavior is always from 2 to 1. So it says from Q2 to Q1. And I also wrote it in this notation as well. As x goes to negative infinity and as x goes to positive infinity, the y values are both going to infinity. Often you'll hear me say that even degree power functions have the same end behavior. That means that the y values are going in the same direction, no matter whether the x values are going to negative infinity or positive infinity. The domain is always negative infinity to infinity. Any x value in that interval will work. And the range, it's always going to be from 0 to infinity, including 0. That's why you see a square bracket at 0. Okay, what if we flip this even degree power function upside down? What if we make the leading coefficient negative? The end behavior, instead of going from 2 to 1, it's now opposite from that. It's now upside down. It's now going from 3 to 4. And if we look at the other way I'm writing it, as x goes to negative infinity, y is going to negative infinity. And as x goes to positive infinity, y is also going to negative infinity. Once again, the y values are going in the same direction. That's why we say it has the same end behavior. Domain is always negative infinity to infinity. The range, however, this time, the biggest y value we could get is 0. and we can get anything less than that. So we'd say from negative infinity to 0. Remember, always smaller number on the left, bigger number on the right, and we want to include 0, that's why square bracket. Each of these even degree power functions, they all have line symmetry. A graph has line symmetry if there's a vertical line, x equals some constant a, that divides the graph into two parts such that each part is a reflection of the other. And that's what this is showing you over here in that image. The graphs of even degree power functions always have that line symmetry right at the y-axis, right at the line x equals 0. Let me just show you that line. Here's the line x equals 0. Let me make it a dashed line. All even degree power functions, let me put this back to like x to the 4, let's say. They all have line symmetry at the y-axis, so at the line x equals 0. Even if I flipped this upside down, it still has the line symmetry at the y-axis. Okay, now let's talk about odd degree power functions. So odd degree power functions in our chart that we filled out would be the degree 1, the degree 3, and the degree 5 functions. They all had the exact same properties as well. Let's look at if we have an odd degree one, like 1 or 3 or 5 or 7 or 9 or so on. They all have the exact same end behavior, and they all have the exact same domains and ranges. They all start down in quadrant 3 and finish up in quadrant 1. Unless I flip it upside down, of course, then we have the opposite. Starts in quadrant 2 and finishes in quadrant 4. But let's summarize the properties of those odd degree power functions. So the end behavior, if the leading coefficient was positive, it went from quadrant 3 to quadrant 1. And if we were talking about it in this notation, we would say as x goes to negative infinity, so let's look down at this graph of an example of one. As x goes to negative infinity, the y values are going infinitely low, so y goes to negative infinity. And as x goes to positive infinity, so as I move to the right on the graph, what's happening to the y values? They're going infinitely high, y goes to positive infinity. Notice how these behaviors of y values are going in the opposite directions. This function is going in opposite directions on either end. So we say these have opposite end behavior. And the domain and range of any odd degree power function, there are no restrictions on either. They go forever left and right and forever high and low. So no restrictions on domain and range for any odd degree power functions. We could fill out both of those now. How about if we make the leading coefficient negative? So if we flip it upside down, here's the example here. Notice it goes from quadrant 2 to 4 this time. So from 2 to 4. And if we write it the other way, as we move forever to the left, so as x goes to negative infinity, the function's going infinitely high, so y is going to infinity. And as I move forever to the right, so as x goes to infinity, the y values are going infinitely low, so they're going to negative infinity. Once again, it's going in opposite directions on either end. These are opposite values, which is why we say odd degree power functions have opposite end behavior. Now let's talk about symmetry of odd degree power functions. They do not have line symmetry. They have what's called point symmetry or rotational symmetry. So these graphs have a point that if you were to rotate the function 180 degrees around that point, you would have the exact same graph. So notice, okay, I've got the same function twice here. These are clearly odd degree power functions. Oh, and I should mention also odd degree power functions have that point symmetry at the origin, at the point 0, 0. So at this point right here, that's where the point symmetry is for odd degree power functions. If I were to take this function and do a reflection across the y-axis to see if it has line symmetry, let me show you that. Let me just reflect this across the y-axis. Let me flip it left, right. Notice it's not the same function anymore. So it does not have line symmetry. But if I were to rotate that function 180 degrees around the origin, watch if I do this, rotate it 180 degrees around that point at the origin. Let me just move it back a little bit here for you. Notice it still looks exactly the same as where it started. So it does have rotational, or what we call point symmetry. Okay, we're almost done. 2 examples to finish it off, and they're going to be quick. So I want you to look at, so I have 8 power functions here. I want you to put them into the right category based on what their end behavior is. And when we're doing end behavior, we're going to be looking at the degree of the function, whether the degree is even or odd. And then we're going to be looking at, is the sign of the leading coefficient positive or negative? And that should allow us to figure out what the end behavior of the function is. Okay, let's think about what functions are going to be from quadrant 3 to quadrant 1. Quadrant 3 to quadrant 1, that means starts down here and finishes up here. So notice it's pointing in opposite directions, which means it has opposite end behavior, which means it has to be an odd degree function, which means the exponent has to be odd. So we are looking for an odd exponent. And then from 3 to 1 would be a positive leading coefficient. So we're looking for functions that have an odd exponent and a positive leading coefficient. Odd exponent, positive leading coefficient. Well, this one has an odd exponent. It's an exponent of 1, and it has a positive leading coefficient. And this one has an odd exponent and a positive leading coefficient. So those two functions are both functions that would start in quadrant 3 and finish in quadrant 1. So we'll put them both there. Now let's talk about from quadrant 2 to quadrant 4. From 2 to 4 means it starts up here and finishes down here. I'm not worried about the in-between part right now. It just starts in 2 and finishes in 4. So once again, that's opposite end behavior. So it has to be an odd exponent, but it's been flipped upside down from the previous one. So that means that the leading coefficient must be negative. So now we're looking for odd exponent, negative leading coefficient. Here's one. Here's another. So we would write those two functions in this spot. Quadrant 2 to quadrant 1. That means starts here and finishes here. Notice it's pointing in the same direction from where it starts and ends, so it has the same end behavior, so that is an even degree power function. So I'm looking for an even exponent, and I'm looking for a positive leading coefficient. So even exponent, positive leading coefficient. Even exponent, positive leading coefficient, I see this one and this one. So we would write those two functions here. And lastly, quadrant 3 to quadrant 4. That means starts down here, finishes down here, pointing in the same direction, same end behavior, means it's an even degree power function, and it's been flipped upside down, so it must have a negative leading coefficient. So we're looking for an even exponent with a negative leading coefficient. Even exponent, negative leading coefficient. That would be that one and that one. So we would write those two functions here. That was the most important example of this lesson. Example 4 is just more practice of the same type of thing. We'll go through it really quickly because I think by now you probably have the hang of it. So for each of these functions, you have the graph and the equation. We should be able to answer it just with either or, but you have excess information for this. We're going to write the domain and range, end behavior, and identify any symmetry. So for this first function, y equals negative x. And keep in mind the exponent on that is 1. It's odd. The domain, no restrictions on the domain for any of these examples. Range, it goes infinitely high and low as well. No restrictions on the range. Odd degree power functions don't have any restrictions on the domain or the range. Now let's talk about the end behavior. This one starts in quadrant 2 and finishes down here in quadrant 4, so it goes from quadrant 2 to 4. Or we could write as x goes to negative infinity, so as I move to the left, the y values are going infinitely high, they're going up to infinity. And as x goes to positive infinity, so as I move to the right, the y values are going infinitely low, so y is going to negative infinity. Part 3 says any symmetry. Yep, there is point symmetry at the origin. All odd degree power functions have point symmetry at the origin. Part B, this is an even degree power function with a positive leading coefficient. Even degree power functions, no restrictions on the domain, but there are restrictions on the range. It never goes below that y value of 0, so we'd say it goes from 0 to, it extends from quadrant 2 to quadrant 1. Or we could write it in the other notation as x goes to negative infinity, what's happening to y. So as I move forever to the left, the y values are going infinitely high. They're going to infinity. And as x goes to positive infinity, so as I move to the right, the y values are going infinitely high. Y is going to infinity. Same end behavior on both sides. Symmetry, yep, this has line symmetry at the y-axis. And all even degree power functions have that. Last part C, odd degree power function, positive leading coefficient. Remember, any odd degree power function has no restriction on the domain or the range. It extends from quadrant 3 to quadrant 1. Or we could write it the other way and say as x goes to negative infinity, so as I move to the left, the y values are going infinitely low. They're going to negative infinity. And as x goes to positive infinity, the y values are going to positive infinity. They're going here. As I move to the right, the y values are going infinitely high. It has opposite end behaviors on either side. And this one, once again, because it's an odd degree power function, has point symmetry at the origin. Okay, that's it for the properties of power functions. We're going to apply all of this knowledge to more complex polynomial functions in the next lesson, where we start adding terms to these types of functions.